Your lecture series starts with Dr. Amit Mahajan. I am going to introduce him briefly to you. Dr. Amit Mahajan is presently working as faculty at Department of Applied Sciences, National Institute of Technology, Delhi, India. He obtained his MSc degree from HP University, Shimla in the year 2004. He obtained his MPhil degree in the year 2006 from Maharshi Dayanand University, Rohtak, and his PhD degree in the year uh, 2009 from NIT Hamirpur. He worked at University of Windsor, Canada as postdoctoral fellow in 2010. He has 62 research publications in various international journals of repute to his credit. He has completed one uh, major research project from CSIR in 2019, and he has guided one PhD candidate as of now. So many are in the pipeline. So I'm handing it over to you, sir. You take over, sir.
Hello. Thank you so much, Professor Markande, and thank you so much for inviting me for this talk. I hope I'm audible.
Yeah, you are audible.
Yeah, sure. So just give me 1 minute to share my screen.
Yeah. Yeah.
Okay. So today I'm going to talk about a very renowned method, which is energy method, and we are going to talk about how to deal with the uh, stability of fluids by using this energy method. So this method was developed long back, and earlier it was used for in vibration or strings, etc. And later it was found that it is very good method to deal with the stability of fluids also. Okay. So to start with, it is important to know why we need to study stability of fluids. Okay. So there is a very famous quote which I am going to read first, that yet not every solution of the equations of motion, even if it is exact, can actually occur in nature. The flows that occur in nature not only obey the equations of fluid dynamics but also be stable. So we know that the flow equations are like continuity equation, momentum equations, but those equations should, if there's any solution, it must be stable solution, and so we need to analyze the stability of fluids, and the stability can be of flow stability, or it can be thermal instability. So we can deal with the flow instability, where we say that the flow becomes from laminar to turbulent, or we can talk about thermal instabilities, where there is a natural change from the conduction to convection. Okay. So how does the instabilities occur is, hello.
Hello. Yeah. Hello.
So how does, hello.
Hello. Continue, sir.
Okay. So how does instabilities occur is another question. So if you have any model, you have any system, then the instabilities generally occur when there is disturbances in the system which distort the equilibrium. Okay. So to just give an idea of how we can say it is stable or unstable, I'm presenting this small picture. Say, talk about what is linear stability and stability. say you have a cup shaped and assume that there is a steel ball at the bottom of this hemisphere. Okay, and if I give some disturbance to this and say that disturbance is of very small quantity, and when disturbances are small, then the product of disturbances, we can say they are negligible. Okay, so then in that case we can talk about that we will have only linear type of stability or instability. So if your disturbance is small and if you have a steel ball at the bottom of this sphere, then that disturbance will move that ball to the side of, and it will distort the equilibrium position. But with time, it is obvious that this ball will take a few oscillations and it will return back to its equilibrium position. Okay, so we say that it is a linearly stable system because the disturbances will die down after some time. Okay, but if you take the hemisphere which is inverted and put a steel ball on top of it, and then if you give a very small distortion or a disturbance to it, then this will not revert back to its original position, and we say that the system is linearly unstable. Okay, but these disturbances are very small. What will happen if the disturbances are large? Okay, so if the disturbances are large, then if there are any product of the disturbances, then those product of disturbances cannot be neglected. Okay, so in that case the non-linearity will also take a major role. And uh, just to show you that even which system which looks like linearly stable, the non-linear terms may destabilize that system due to large disturbances. Okay, so this system which looks like stable linearly for small disturbances, maybe actually the non-linear terms may destabilize this system. Okay, and the system which looks like unstable, actually the nonlinear terms can make that system stabilize. Okay, so nonlinearity plays a very important role when we solve the flow problems or thermal problems. Okay, so we need to tackle not just the linear terms but also the non-linear terms, and that's where the this energy method has played a very important role. Because we know that we can solve the linear system by say normal mode technique, but that technique do not work when we have non-linear terms present. So there is a very very
Sir,
nice
sir,
energy method. Yeah, yes sir.
hello. Sir, your slides are not visible to many participants here. They're sending the message. Just you can switch it off and you can on the system, I believe.
Okay, okay, no problem.
Okay. Okay.
Hello.
Sir,
Is it
now
visible
it's
now?
visible, sir. Now, yes, sir. Yes, sir.
Right.
Okay. Thank you.
Okay. So this is what we are saying, that the system can be destabilized, which is linearly stable, or can be stabilized even if it is linearly unstable. Okay. So I'm going to illustrate this famous method of energy and how to use this method for the fluid equations. And to start with, I'm going to take very simple equation of diffusion, and then we'll add a linear source term to that diffusion equation, and we'll see how much difference just one source term can add to this method. And then I will also go by the Bernard problem for thermal instability, and add an idea of Joseph's coupling parameter to it. And then I will also show that how we used the generalization of this method on these special fluids, magnetic fluids. So take this first example, the very famous diffusion equation, and how we can utilize the method of energy to see whether the diffusion equation is stable or not. Okay, so consider this one dimensional diffusion equation uh, of length 1 unit. Okay, and with the boundary condition that uh, at x0 the u value is 0 and x is equal to when u value is 0. So at both endpoints the u value is 0. So you can like assume that there is a one dimensional rod of one unit length, and u can be considered as the temperature. So this is like a heat equation for the rod with the temperature at both ends to be exactly 0. So what we want to know is if there is a solution to the system, so then this solution is stable or not. Okay, so that's what we want to investigate. Okay, so I'm saying a zero solution, but the initial solution can be a non-zero solution also. But if you know the base solution, then the idea is to whether that base solution is stable or not. That means if we disturb that base solution, if we give some disturbances to that base solution, whether those disturbances will die down with time or not. Okay, so to do this, what we do is we find the base solution for this example. Say u equal to 0 be the base solution, and then we perturb this system. That means we assume that the base solution is disturbed, and because these equations are linear, so if I put the disturbances here and use the base solution, so I will get the same system as a disturbed equations. Okay, so how to generate now the energy for the disturbances? Okay, so what we do is that we know that this is the heat equation. So if I multiply both sides of this equation with this u and integrate over with respect to x over the limits, which is 0 to 1, then I can easily rewrite this equation. Okay, so I'm multiplying the heat equation with u on both sides and integrating with respect to x 0 to 1. Okay, so on the left hand side there is a time derivative. So this u dot del du by dt, I can write it as a derivative of t of u square. Okay, and on the right hand side it's a product of two terms, so I can use integration by parts with u as first function and the second derivative term as second function. Okay, so just do these two steps. So this left hand side I can write as half of derivative of t of u square, which is same as u dot del du by dt, right? And on the other side we use integration by parts. So a first function derivative integral of second function minus integral of derivative of first and integral of second. Okay, so and because the u function is 0 on both boundaries, so this first term on the right hand side will be 0, and so I can easily write this uh, that the left hand side half constant and the time derivative and integral interchanged, and this is derivative ux squared. Okay, and then we define them in terms of norms. Okay, so in L2 space, if we work in L2 space, then this integral 0 to 1 u square dx is this L2 norm u square, norm of u square. And similarly the right hand side integral can be written as norm of del u by dx square. Okay, so the left hand side, if you look at this, it is a derivative of half u square. So I can write this as derivative of e of t, where et is half of u square is the energy of disturbances. This energy is the kinetic energy. If you remember the formula for kinetic energy, it is half mv square, half into m into v square. And m is not present in the sense that the system is dimensionless. Okay, so we can assume that the mass is non-dimensionalized. Okay, so it is kinetic energy half v square. Okay, and on the right hand side it is minus of norm of del u by del x square, and we know that norms are always positive, so right hand quantity is negative quantity, so this force will be a stabilizing force. Okay, so the evolution of kinetic energy with time, or evolution of energy with time, is uh, on the right hand minus of this stabilizing term. Okay, so this stabilizing term, and this energy is the energy of disturbances. So idea is that what happens to this energy with time. If we can show that with time this energy goes to zero, that means the disturbances die down. Okay, so I'm just rewriting this equation on the new page. Okay, and to show that we solve this equation, we use a very famous inequality which is called the Poincare inequality, and that can be used because the u value is 0 on both endpoints, and it says that the norm of del u by del x square is always greater than equal to pi square times norm of u square. So if I substitute it in this equation on the right hand side, then the change in energy with time can be easily written in terms of the energy, because of this inequality it is minus pi square u square, and u square I can substitute back from this equation as 2 times e. Okay, so the change in energy with time is minus 2 pi square et, is less than this. Okay, now if I take this to right, the left hand side, and combine these two terms, then I can write it as a derivative of a single term, and then if I integrate this, then easily I can calculate the energy at any time. Okay, so is the energy of disturbances at any time, and it is always less than the initial energy times an exponential factor of time. And you can see that when time grows, this exponential factor slowly dies down, or it goes to zero. So it easily proved that the energy of the disturbances actually grows to zero, at least exponentially fast. Okay, so and we can say that this system is stable, because whatever disturbances we gave, the energy produced by those disturbances actually becomes zero after some time. Okay, so that means the system is actually stable. Okay, now this was heat equation. I just add a source term to this. Okay, so you have a heat equation, and I added a source term to this with a positive. Okay, and with the same boundary condition, the idea is again to see whether this will be stable or not. Okay, so say u is equal to 0 is a solution to this system, and we want to again investigate whether this zero solution is stable or not. That means we are going to disturb this system, and then create the energy for the disturbance, and see what happens to the energy with the time, as time progresses. Okay, so again the method says that you multiply with the dependent variable on both sides and integrate over whatever range is there. So if I multiply with u on both sides and integrate with respect to x from 0 to 1, then I can write that the left hand side equals to this right hand side. Okay, and for this first term we know how to deal with the time term. Now we can write this as half of time derivative of u square. We know how to deal with this term. We use integration by parts to this term, and the third term is already a norm of u square, so there is nothing to be done with this third term. Okay, so it just use all those steps again. Okay, and write that it is half of time derivative of u square minus del u by del x square norm, which is this first term, and the last term, the source term, becomes a times norm of u square. Okay, the left hand side again, it is a half of velocity square, so we can write it as energy. Okay, so we can define that it is the evolution of disturbance energy is equal to this right hand side, where energy is half of norm of u square. Now in this particular case, the first term is a negative of norm square. Okay, so this is a stabilizing term, but the second term is, because norms are positive, a we said is positive, so this is a destabilizing term. So there is a competition between the stabilizing and destabilizing term. Okay, so if this destabilizing term will be bigger than this stabilizing term, then this energy will decay. Okay, but if this destabilizing term will be bigger than uh, stabilizing term, then the energy will not decay, because but there will be an instability. Okay, so with the usual way, if I solve this, if I apply Poincare inequality on this, then I can easily write this as minus pi square norm of u square. And if I take norm u square common, then inside the bracket I will have uh, pi square minus a with a negative outside. So immediately I can say that if a is less than pi square, then I will have a stability, because then this term will be the second term will be less than the first term. Okay, if a is less than pi square. Okay, so, but we are not going to do this this way, but we are going to illustrate it in a more general way, that whenever you have a stabilizing term and you have a destabilizing term, then what we do is we take the this stabilizing term outside, and we write it in a particular form. Okay, so just rewriting the right hand side in this form. Okay, taking a norm of del u by del x square outside as a common, so that the terms inside the bracket becomes this 1 by a minus norm of u square over norm of del u by del x square. Okay, so this is the ratio of uh, the destabilizing by stabilizing. Okay, and there's a positive terms outside with a negative sign. So if this term inside the bracket, if it is positive, okay, then this whole quantity will become a stabilizing term. Okay, so if I assume that this is a positive quantity, and then this will become a stabilizing term and energy will decay. Okay, so just to generalize this, because in fluid mechanics we have number of more terms, uh, this second term will always be less than its maxima. Okay, so I can use an inequality that this term is always less than equal to its maximum value. Okay, and then we define this maxima as 1 by re as maxima of this numerator by denominator. Okay, and then we substitute it back here to rewrite that the change of energy with time is minus a del u by del x norm square times 1 by a minus 1 by re. So we what did is this, we just substituted this as 1 by re, and still the point is same, that if this 1 by a minus 1 by re, if it is positive, then this whole quantity on the right hand side will be a stabilizing and the energy will decay. Okay, so to make energy decay, we immediately have this result from here, that if 1 by re is less than 1 by a, and then I can use Poincare inequality on this to show that energy will decay. Okay, so we'll just do this, that when a is less than re, that means this quantity is positive, say this quantity is c, then the last inequality can be written as this, the bracketed term is substituted as c now. Okay, and on this norm derivative square, we know we can apply Poincare inequality, and so we can write that this is less than equal to pi square u square. Okay, and the u square is 2 times energy. Okay, so as by definition, so again we are at the same type of equation, which we can solve by taking it to left hand side, uh, writing that as a single derivative of time and integrating. Okay, so we write it as a derivative of time, integrate it with respect to t, to write that the energy at any time is in less than initial energy times an exponential factor of time. Okay, so when time grows, this exponential goes to zero, and so energy will decay. But now this decay is conditional, because there is a condition generated that a must be less than re, where we have defined re as a maximization problem. Okay, so there is a energy decay, that means the disturbances are dying. Okay, and the system is stable, but that stable is with this condition, which is a less than re. So if we can calculate the value of re, then we will know that what is the maximum value of a, or what is the maximum source heat source we can give to the to that heat problem. Okay, so how to calculate this re? So to find re, we recall that we define re as a maximization. Okay? And we can use the calculus of variation and use Euler-Lagrange equations to solve this. Okay, so if I define I1 as the numerator, which is norm u square, and I2 as the denominator, which is norm of del u by del x square. Then Euler-Lagrange equation for this maximization is change in I1 minus change in I2 is equal to 0. And change in I1 means I1 is already there. So change small, any change in this will be u plus epsilon time a function, and change in this will be del u by del x plus epsilon time a function. Okay. So del I1 will be a change in u. So this norm square, we know it is integral of u square. So change in del I1 will be integral u changes to u plus epsilon eta squared, where eta is a function similar to u. Okay, and then its derivative with epsilon at epsilon equal to 0. Similarly, change in I2 will be, this norm is written in terms of integrals, and it will be del u by del x plus epsilon del eta by del x, uh, derivative with epsilon at epsilon 0. Okay, where this eta will have the same conditions on as on u, because u was 0 on both boundaries, so eta will also be 0 on both boundaries. Okay, so the idea is that we can calculate this del I1 from here and del I2 from here, and we substitute it back here. And because eta is arbitrary function, so we will get a differential equation from here, which we can solve to find Re. Okay, so let us find what is delta, this del I1. So we can different, because integration is with x, so we can take derivative with epsilon. So it will be 2 times u plus epsilon eta times the derivative of inner, which is eta, and then we can put epsilon as 0. So it will be 2u eta. Okay, so del I1 is nothing but integral of 2u eta dx, where u and eta are both functions of x. Okay, and similarly we can calculate del I2. We can take epsilon derivative and then put epsilon 0. So we'll find del I2, and then we'll substitute both of them back here. Okay, so for del I2, so if I differentiate this with epsilon, this is a whole square, so it will be 2 times this quantity times the derivative with epsilon of inner, which is del eta by del x. Okay, then put epsilon 0, so this term will be 0, and we'll have del u by del x times del eta by del x. Okay, so we'll get this quantity. And in this we can use integration by parts, with the del u by del x as first term and del eta by del x as second term. And so first term integral of second minus derivative of first integral of second. And because eta is 0 on both boundaries, the first quantity will be 0 and the second quantity remains. Okay, so we can substitute now this del I1 and del I2 value back in the Euler-Lagrange equations to write that this integral holds. And because this integral holds for arbitrary eta, so this will be equal to 0 only if the term inside the bracket here is equal to 0. Okay, so since eta is arbitrary, this differential equation must be satisfied. Okay, and this differential equation, we know it is along with two boundary conditions, that u0 is 0 and u at 1 is 0. So we can assume a solution like constant times sine and pi x, substitute that solution here, and then we can calculate Re value. And if you calculate this, you will find that Re value is equal to pi square. Okay, Re will come out to be pi square, 2 pi square, 3 pi square, and so on. So the Re must be equal to pi square, so that the A is less than pi square is satisfied. Okay, so this is, I'm not going to solve this differential equation. The idea is to how to create how to show that energy decays with time, and how to use calculus of variation to find the corresponding differential equation. Then its solutions are simple. You can use any method to solve them. So this was a heat equation with a source term. Okay, now I take or generalize this method to the fluid problem, and we start with the classical Bénard problem, which says that if you take a horizontal layer of fluid which is heated from below. Okay, so if you take a horizontal layer of fluid which is heated from below, then due to heat, the lower part of the layer expands, and if the temperature gradient or the layer depth is sufficiently large to overcome the effect of gravity, then the fluid start rising. Okay, so the conduction state will change into a convection state, and a cellular motion pattern will be seen. Okay? So it's a classical Bénard problem, and for this we need the equation of continuity, the equation of momentum, and the temperature equation. Okay, so the system which defines this Bénard problem is this continuity equation, where Q is the velocity, okay, and the fluid is incompressible. The momentum equation, okay, where we have mu as viscosity, T is the temperature, alpha is thermal expansion, and the gravity is acting vertically downward. And there is a energy equation, the temperature equation, and both the boundaries, the lower plate is kept at a fixed temperature TL, and the upper plate is kept at a fixed temperature TU, and the lower temperature is greater than the upper temperature. So this is the typical Bénard problem. And the first step is to find the solution or the steady state or basic state. And for the Bénard problem, we know that the solution was given by this, that the fluid is at rest and there is a temperature flow as a conduction. Okay, uh, and then we can find the basic density, and we can also find the basic pressure, but I'm not writing that here. Okay, because in typical heat transfer problem, this pressure term gets eliminated at a later stage. Okay, so once you have this basic state, then the idea is whether the basic state is stable or not. Okay, so to find the stability, we disturb the system, that we take perturbations to this. So this velocity will be perturbed, temperature will be perturbed, density will be perturbed, and pressure will be perturbed. Okay, so if we perturb this system, then take that the basic state we add a perturbation q dash. Similarly to density, we add a perturbation. To temperature, we add a perturbation change as a theta, and so in pressure. And if we substitute back this in the original system and use the basic state equations, then we can write the perturbed equations, which are written now in non-dimensional form, where a non-dimensional parameter r, which is a Rayleigh number, which acts as a control parameter for the system. We know that these three equations are the equations for the disturbances. Okay. Now the idea is to find whether these disturbances which are generated will actually die down or not, and for that we will construct an energy. And how we construct an energy is we multiply the equation on both sides with the dependent variable. Okay, so here in the first seventh equation, the dependent variable that we are going to multiply both sides is q, and on this equation it is theta. Okay, so for construction of energy, you multiply this seventh equation on both sides with q, and multiply ninth equation on both sides with theta, and then integrate these equations over the volume, because we are working in now 3 dimensions. Okay, so instead of integrating over a line, we are integrating over a volume. Okay, so so if you multiply on both sides, can I just go back on q to this equation, and then we know how to deal with the time term. It can be written as half of time derivative of q square. Okay, this if you use integration by parts, or in 3 dimension we say that we use Gauss divergence theorem, this second term will become 0. Similarly, the pressure term will become 0 on using Gauss divergence theorem or integration by parts. This term, when we use Gauss divergence theorem, one gradient will go to other q and it will become del q norm square. And when q is multiplied here, it is unit vector, so it will become w theta, because w is the third component of velocity q. Okay. Similarly, we do theta multiplication and integrate this. So we can write the equations in terms of norms, and you can see that there is a derivative with time, and on the right hand side there are these are integrals or inner products, and there are norms, and norms are always positive, and inner products can be positive or negative. Okay, so we now construct the energy, and in this case there are two energies, one due to the velocity and other due to the temperature. Okay, so the energy is kinetic energy for thermal and the kinetic energy for the velocity. Okay, so half of theta square plus half of q square, so sum of these two energies will be the total energy. Okay, and So if I substitute, if I differentiate this with respect to time to find the change of energy with time, and then substitute these two quantities from here, then I can easily write dE by dt, the evolution of energy with time, as time derivative here, and then put that from 10 and 11 to write it as I minus d, where I are the inner products which we are calling energy production terms, because they can be positive or negative. And d are norms, and norms are always positive, and they are occurring in the equation with a negative sign, so they are always acting as a energy dissipating terms. Okay, so the change in energy with time is actually energy production terms, those are destabilizing terms, and energy dissipative terms, those are stabilizing terms. Okay, so again on the right hand side there is a competition between the uh, destabilizing and stabilizing terms, and then the method says that if I take the stabilizing term common outside, so if I take minus d common on the right hand side, and then I can write it as minus d times 1 minus I by d. Okay, so just rewrite that I minus d as minus d 1 minus I by d. Okay, and then because this I by d will always be less than equal to maximization of this. Okay, and we denote this maximization as m. Earlier we denoted by 1 by r, if you remember. Okay, so this will be 1 minus m, and if this 1 minus m is positive, okay, if we denote it by a naught and take a naught as positive, then I can write that the evolution of energy with time is always less than minus a naught d, where this right hand side is a energy dissipating terms. That means they are stabilizing the system. So now I can easily prove that the energy will decay with time, and this energy decay is conditional, because this 1 minus m has to be positive. That means m must be less than 1. Okay, and we have m as maximization problem. Okay, so we can calculate that value. So okay, so how to do this? Now we know what is d. D are these norms. Okay, and we use Poincare inequality again to write that the norm of del theta square is greater than pi square theta square, and similarly norm of del q square is greater than pi square q square. And if I take pi square common, then theta square plus q square, and that's what we define energy. Okay, energy is half of theta square plus q square. So theta square plus q square can be written as 2 times z. Okay, so if I substitute this back here, then the evolution of energy with time can be easily written as minus 2a naught pi square e. Okay, so now we know how to solve this. Take this to other side, combine the time derivative and integrate. Okay, so easily we can do this in 2 steps, and we can prove that the energy at any time is always less than the initial energy times the exponential factor of time, and as time increases, this energy, which is energy of disturbances, it decays with time. That means the system is always stable. Okay, now this decay is conditional because m should be less than 1, and this maximization problem is to be solved for this. Okay, so how to solve this is by using Euler-Lagrange equations. Okay, we use calculus of variation. So maximization of I by d, and I and d are well defined by those equations. I was the integration terms, and d was norms. Okay, so if you use calculus of variation, the Euler-Lagrange equation, which is now del I minus del d equal to 0, because we are solving for m is equal to 1. That means r is equal to 1 if you look at the previous picture. Okay, and del I is change in I. Okay, so it is w time theta. So it is w change in w. So w plus epsilon h3, and change in theta. So theta plus epsilon eta. Okay, so change in w and change is eta. Derivative with epsilon at epsilon 0. Okay, and similarly change in d means change in this norm square and change in this norm square. So change in theta we said is eta, so change in del theta is at del theta plus epsilon del eta square, and similarly change in del q is del q plus epsilon del h square. Derivative with epsilon at epsilon 0. So now we can take derivative of this, we can apply product rule here, and then put epsilon 0 to find del I. Similarly, we can take derivative here, put epsilon 0. Okay, so it is very simple. Okay, take derivative with epsilon. We have to use product rule here. Okay, so first function derivative of second, which is eta, plus second function derivative of first, which is h3. Put epsilon 0, so we'll get only 2 times w eta from here and theta h3 from here. So del I is calculated as this. Okay, similarly we can calculate del d, take epsilon derivative of this. Okay, so it's the integral square, so 2 times del theta plus del eta times the derivative of inner, which is del eta. Okay, similarly on this, 2 times the quantity times the derivative of inner, which is del h. Okay, put epsilon 0, and then we can easily write that del theta into del eta, because this term will be 0. Okay, similarly del q to del h. And then here instead of eta we have del eta, and instead of h we have del h. So we can use Gauss divergence theorem or integration by parts on this to write that it is minus 2 integral of del square theta eta minus 2 del square q of h. Okay, remember that eta and h satisfy the same boundary condition as theta and q. Okay, eta will satisfy the same boundary condition as theta, and h will satisfy the same boundary condition as q. So if we substitute these back in the Euler-Lagrange equations, then because eta and h are both arbitrary, so the terms for h will combine and must be equal to 0, and terms of eta must combinedly be equal to 0. Okay, so that gives us a system of differential equations along with the boundary condition on velocity and temperature. So we can use a solution to solve this. Okay, and this is a homogeneous system of differential equations, and for a non-trivial solution the coefficient matrix determinant must be 0, so we can use that to find this control parameter r. Okay, so that is the value of Rayleigh number, which was calculated for the Bénard problem by this method. Okay, so this was the energy method applied on Bénard problem. Now I add to this the idea of coupling parameters. Okay, so this was introduced by Joseph in 1965-66. Okay, and 2 papers are referred here. Okay, so the idea is that while construction of energy, we said energy is half of velocity square plus half of temperature squared. Okay, so just show you back those equations. Okay, so these were the 3 equations for the disturbances, and then we constructed by multiplying q and energy equation, and we multiplied with theta to temperature equation to create this thermal equation. Okay, and then we defined energy to be half of q square plus half of theta square. But that means that the amount of energy produced by heat is and the velocity are in the same proportion. Okay, so if there is a 50% of heat energy produced, then there is a 50% of fluid energy, this velocity energy produced, kinetic energy of fluid. Okay, but Joseph said that the energy may be different. Okay, so he added a idea of coupling parameter, that instead of adding the two kinetic energy, he added a parameter lambda, so that this will this value of this will be calculated later after calculating Euler-Lagrange equations by an optimal method, and this will tell that how much disturbance of fluid energy and thermal energy are in the ratio. Okay, so they are not equally contributing to the total energy, but in some ratio dependent on this value of lambda. Okay, so the process remains the same, but there is a new parameter lambda added, which we call as a coupling parameter. Okay, and it is always positive, and its value is calculated at a later stage. Okay, so with this energy, again the evolution of energy, we can write the same thing with I and D, only due to lambda these changes are there. Okay, if lambda is not present, here was 1, then it was 2, and it was 1. Okay, so the same process remains the same, but a coupling parameter lambda added to the system. Okay, and then easily we can prove thus with the same process that the energy decays with time exponentially. The only thing is that lambda needs to be calculated using the maximization problem, because lambda exists in the I and D terms. Okay, so I skipped it very quickly because the process is very similar to Bénard problem, only the parameter is added. Okay, and then you can use the same Euler-Lagrange equations. Okay, calculate these derivatives with I and D. Okay, with the same method, and lambda is a fixed number as a constant. Okay, so we can calculate delta I, and similarly we can calculate the delta D, and then we substitute in Euler-Lagrange equation, and we find that the differential equation is now actually have two parameters, R and lambda, instead of single parameter R. Okay, so we can solve this differential equation because boundary conditions are there. We can assume a solution and solve with the dispersion relation. But in this case, we will find that R will be a function of lambda. Okay, and then we can find the optimal value of R by finding the optimal value of lambda using the maximization minimization principle. Okay, so that part I'm not describing in this lecture, but you can always go through these in the Joseph's paper, and they have described it very well. Okay, how to solve this further. So this method we used and we generalized this method to a very complex problem on magnetic liquids. And magnetic liquids, as we know that they are artificially synthesized, and its first synthesis was done by NASA in the 1963, and it's a liquid which gets highly magnetized in the presence of a magnetic field. Okay, so this model which I'm taking, this model was first solved by Finlayson using the normal mode technique, using linear analysis, and we applied this energy method to this problem, and we published a work in 2008. And this model requires a continuity equation, a momentum equation with the additional force due to magnetic body force term, the energy equation, the Maxwell equations for the magnetic field, and a equation of magnetization which is taken similar to what Finlayson did. Okay, I am saying this particularly because there are different magnetization equations exist in the literature, and we particularly used exactly what Finlayson used. Okay, so again, the idea was simple, that you find a base solution to this. Okay, and then disturb the system and see whether the disturbances will die or not. Okay, so we found a base solution, and then we disturbed the system, and the disturbed system in non-dimensional form is written as this. Okay, so here we have a nonlinear term on the left hand side, and there are these nonlinear terms on the right hand side, which are due to the presence of magnetic field, or due to only in magnetic fluid these terms arise. Okay, where M1 and M3, they are magnetic parameters. R is the Rayleigh number as used in the Bénard problem. Okay, so there is a continuity equation, temperature equation, and there is a magnetization equation. Okay, so the idea is to find first formulate the energy. So method is again the same. You multiply the equation of momentum both sides with Q and integrate, multiply the equation of temperature both sides with theta and integrate, multiply the equation of magnetization with both sides with phi and integrate. Okay, so once we do that step, then we can write these equations in terms of norms and inner products. Okay, then we can define the energy and rewrite this as evolution of energy, dE by dt equal to something. Okay, so I'm going to rewrite that. Okay, so we defined energy as half of theta square, plus we added a coupling parameter lambda 1 times Q square, and another coupling parameter lambda 2 for the magnetic equation. Okay, because there is no time derivative in the magnetic equation, so no term in the energy for phi comes. Okay, and then the evolution of energy can be written as sum of three terms instead of two, where I naught are inner products with two factors. Okay, and because these are positive or negative integrals, so we call them energy production terms. Okay, D naught are norms, and because norms are positive, so these are energy dissipating terms because of minus D naught sign here. And N known are the higher order nonlinear terms. Okay, so these are also energy production terms. Okay, so if we have to prove that energy decays with time, then we must show that the uh, combined effect of I naught and N naught, which are energy producing term, must be less than D naught, which is energy dissipating term, so that the system is stable. Okay, but when we solve this, then these nonlinear terms uh, are uh, having more energy, you can say. We were not able to directly solve and show that these are less than D naught. Okay, so instead we generalized the method and we added a complementary energy to the system. Okay, so we constructed a more generalized energy as Vg, which is sum of two energies, one the original energy plus another energy which we said is the complementary energy, and which is also calculated in a similar way. So we found I1 D1 N1 for them, and so the evolution of this generalized energy is the evolution of this energy plus the evolution of the uh, complementary energy. Okay, so and the first two term here, I naught minus D naught, we know how to deal with them. We can take minus D naught common and we can write them as minus A naught D naught with M as maximization. So this we know by Benard problem. So now the idea was that there are two D naught and D1. Okay, so D1 is also a dissipating term. So there are the total dissipation energy is D naught plus D1. Okay, and we need to prove that the energy production terms I1, N naught, and N1, their total energy produced must be less than D naught and D1. That's what we proved in this result. Okay, so we gave the estimation. These are I1, D1, and N1. Okay, we gave the estimation of I1 first. This is a energy production term, and we use the Cauchy-Schwarz, Young inequalities, and Embendick theorems to prove that this energy produced is always less than some constant times the D1 plus some constant times D naught. Okay, where D naught and D1 are dissipating energies. And if I choose epsilon naught square as half and B naught in such a way that this quantity
Okay.
becomes A naught by 2.
Ayo,
Hello. And we define the total energy dissipating as D2. So because D naught and D1 were the dissipating energies, so D2 is the total energy dissipated by the system. And we were able to prove that the energy production term I1 is less than the total energy dissipated by the system. Similarly, we gave the estimates for N naught and N1. N naught and N1 were non-linear production terms, and we proved that they are some constant times the D2, the total energy dissipated times Vg half, the generalized energy. Okay. Similarly, is for N1, where these M1, M3 magnetic parameters and other terms are known, and there is a constant C star which came due to an inequality used as given in Galdi and Strongen. So more details of this constant and its value is given in this. Okay, and then we substituted I1 N naught N1 back in the equation to write that the evolution of generalized energy with time can be written as this. Okay, so this is very similar equation, minus energy dissipated into something in bracket. If this quantity in bracket is positive, then this energy will decay. Okay, and here this A cap is a constant which is given by this equation. Okay, so if this quantity is positive, okay, in the bracket, then we can show that energy decay is there. Okay, so we showed a theorem. We write a theorem here that whenever m is less than 0, lies between 0 and 1, m is the maximization of I naught by D naught. Okay, so whenever m is less than 1, okay, and whenever the initial energy is less than a raised to power minus 2, then the generalized energy at any time can be given by this equation. It is always less than the initial generalized energy times exponential factor of this of time. And because of this inequality 22, the term inside the bracket here is positive. So when time becomes large, this exponential term will die down, and so the generalized energy will die down to 0. So any disturbances, okay, so any disturbances to the system will die down under these two conditions. Okay, and because the A can be the value of A is known, so initial energy, what should be the initial energy that can be calculated, and the value of the Rayleigh number we can calculate from this inequality, because M is maximization of I by D, so we can use Euler-Lagrange equations again and convert that into a system of differential equation and solve. Okay, so this was how we use energy method to solve fluid dynamics problems. Okay, so I end this talk here. Over to you, sir. Hello.
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 Am I audible?
Yes, sir.
Yeah. I'm very much grateful to Amit. That was indeed a wonderful lecture. I hope all the participants have enjoyed that. If you have got any doubts, I keep 5 minutes for question and answer. One question is there, sir, in the chat box. How to interpret physically fluid energy in Benard problem? How to interpret physically fluid energy norm Q in Benard problem? That was a question asked by Chinnaswamy Kanchana.
So, yeah. So as I said that we know that kinetic energy is half mv square, half mass into velocity squared. Okay. So because we are saying that physically dimensionless, we are taking the variable. So mass is not there. So half of velocity squared. Okay. And so half of norm of q square. Norm q is the velocity, right? So norm of q square is velocity square. So it's like kinetic energy of fluid, kinetic energy of liquid. Similarly, if we define half of norm theta square, so it is kinetic energy for the temperature, okay, or heat. So this way we can interpret this, that they are kinetic energies basically.
Hello.
Hello.
Kanchana, I think you got the doubts clear?
Yes, sir. Thank you so much, sir.
Okay. So, any more questions? Let me give 2 minutes of time. Mohan, there is a question from Mohan Krishna, I believe. Please ask, sir.
Sir, good evening. The talk by Dr. Amith Mahajan was really appreciative. We could get many of the aspects pertaining to fluid dynamics. Sir, presently, how is the research prospect in this area? Can we
Mohan Krishna, can you
this
on your
particular
video?
area?
Can you on your video? Switch on your video, Mohan Krishna, sir.
Yeah. Am I visible?
Yeah.
Dear sir, how is the research prospect in this area? Can we recommend this particular area for the budding researchers?
Yes, sir. See, as I mentioned that Benard problem, if you know that Benard problem was done in 1900, and Lord Rayleigh solved the Benard problem in 1916. Okay, but this energy method was applied in 1965 by Josephs, and in last 40-50 years there is so much research is going on this topic, and there are many different configurations. As Benard problem is only for the horizontal layer, you can also take a vertical layer or a layer of different form. There are different forces that we can take. For example, we apply to magnetic fluids, there is a magnetic field. Similarly, there can be chemical reactions and so on. So there's enormous scope of work to be done in fluid dynamics with the stability problems. There's there's a lot of work which is still to be done.
Thank you, sir. Thank you very much for the information.
Any more questions? Let me wait for another 1 minute because people started asking questions. So I'll give 1 more minute, sir. I don't, Dr. Amit, can you spare another 1 or few minutes?
Yes, sir, I am here, no problem.
Anyhow, this is one of the most esoteric topics you have taken. So we should be really grateful to you for selecting such a wonderful topic, sir. Thank you.
Thank you, sir.
Thank you, Mohanji. Thank you.
Thank you, sir. With this, I'll conclude the session. I hope all of you have enjoyed his lecture. If you have, certainly you can pose those questions to me. I'll pass it on to him. Not an issue. Thank you, Amit, despite your busy schedule, because your actual schedule was tomorrow, but I preponed it because of some other problem. You have cooperated with me. I'm really grateful to you, Professor. Thank you, sir. I want you to come to SAPTHAGIRI and give us the lecture. So we shall hope it will happen soon. These pandemics will end soon, and we shall hope to see you soon in Bangalore on certain occasions. Thank you, sir. I'll close the session. Thank you.
Thank you. Thank you so much. Thank you so much, sir. Thank you for inviting.
Okay. Participants, please see the mail to yes. Today I have already mailed you. So wait for the tomorrow's. I have made you the link for the tomorrow's session. Please join us at 10 o'clock tomorrow. Thank you. Have a nice day. Thank you. See you tomorrow.
Thank you, sir. Thank you very much. Thank you.
Okay. Bye.